Today's video, we're going to explore two key concepts in computer science, binary trees and binary search trees, as well as the different types of binary tree traversals. We'll break down what they are, how they work, and most importantly, where and why they're used in real-world applications. Binary trees and binary search trees, explained. What is a binary tree? A simple binary tree structure. Let's start with binary trees. A binary tree is a tree-like data structure where each node has at most two children, typically called the left child and the right child. A simple binary tree, showing a root and two children. The topmost node is called the root, and each node can have either no children, one child, or two children. This structure allows for efficient searching, insertion, and deletion operations. It's a very common and fundamental data structure used in computer science. Tree structure with nodes showing a typical binary tree. Root node, left child, right child, narrator. For example, imagine a simple tree of numbers. If we insert 5 as the root, and then 3 and 8 as the left and right children, respectively, we get a basic binary tree. The key idea is that each node can branch off into at most two other nodes. What is a binary search tree, BST? Transition to highlight a binary search tree. Now, let's talk about binary search trees, or BSTs. A binary search tree is a special kind of binary tree, where each node follows a specific property. For every node, the values in its left subtree are smaller, and the values in its right subtree are larger. A binary search tree with the nodes being added one by one. Here's an example. If we insert 5 as the root, and then 3 and 8 as its left and right children, we follow the rule that any number to the left of 5 must be smaller, and any number to the right must be larger. A binary search tree. Root equals 5. Left child equals 3, smaller than 5. Right child equals 8, greater than 5. Because of this ordering property, BSTs allow for fast operations, such as searching, inserting, and deleting elements. The importance of balanced trees. Unbalanced versus balanced tree. But, there's a catch. If the tree is not balanced, performance can degrade. For example, if the tree becomes like a linked list, with each node only having one child, operations could take as long as n, where n is the number of nodes in the tree. Comparing a balanced tree versus a skewed, unbalanced tree. So, it's essential to maintain balance in a binary search tree. There are special types of BSTs, such as AVL trees or red-black trees, that automatically keep the tree balanced after every insertion and deletion, ensuring optimal performance. Binary tree traversal. Transition to the concept of binary tree traversal. Next, let's dive into binary tree traversals. Traversal refers to visiting each node in the tree in a specific order. There are three primary types of traversal you should know about: pre-order, in-order, and post-order. Animated graphics illustrating each traversal type. Pre-order traversal. In this traversal, you visit the root node first, then the left subtree, followed by the right subtree. Visual showing pre-order traversal. Root right pointing arrow left, right pointing arrow right. Pre-order traversal is useful when you want to process a node before its children, for example, when creating a copy of the tree. In-order traversal. Here, you visit the left subtree first, then the root, and finally the right subtree. In-order traversal. Left right pointing arrow root right pointing arrow right. In-order traversal is particularly important for binary search trees because it visits the nodes in sorted order. This makes it ideal for printing elements in a sorted fashion. Post-order traversal. In this case, you visit the left subtree first, then the right subtree, and finally the root. Post-order traversal. Left right pointing arrow right right pointing arrow root. Post-order traversal is commonly used in scenarios where you need to process the children of a node before processing the node itself. This is often used in tasks like deleting a tree or performing a post-order evaluation of an expression tree. Applications of binary search trees and traversal. Transition to real-world examples and applications. Now that we understand the structure and traversal methods, let's take a look at how binary search trees and traversals are used in real-world applications. A search engine interface. Efficient searching in databases. One of the most common uses of binary search trees is in databases. When you need to search for a record in a large database, a binary search tree can reduce the time it takes to find the record, thanks to its fast search properties. This is especially important when managing large amounts of data. A file system with files organized in a tree-like structure. File systems. Many file systems use tree structures, and sometimes binary search trees, to efficiently store and retrieve files. With a BST, finding a file or directory becomes a quick task, even when dealing with large numbers of files. An autocomplete search feature in an app. Autocomplete and suggestions. Have you ever noticed how quickly search engines or apps suggest results as you type? This is done using binary search trees or similar data structures to quickly find and rank suggestions. A decision